Grazie mille Maria per la sua gentilezza. Sono molto onorato parlare qui del monitoraggio e vorrei spiegare come il monitoraggio potrebbe aiutare all'incremento della resilienza. Vorrei spiegare in inglese, naturalmente. Actually, this talk is maybe much more than simply an overview of research. It also has to do with technology transfer, and also I would like to share with you the experience we have at the national level within these competitiveness clusters. The idea is not only to transfer research from academia to companies, to the industry, but the idea is also to co-create a new knowledge that the companies will be able to use straight away or a few years after a project are finished. And this is the initiative which was launched in 2006, so it's relatively recent, and it gave rise already to, hundreds or even thousands of projects all over the country. And well, the idea is that, also the format is that these partnerships are private-public. The industry is usually the driver, and of course, the research and the development and test is done based on public funds. So it's industry-driven with public funds, so to speak, almost. So I would like to give you a brief overview of several research topics and research advances. And this is joint work with many people, including, I'm happy to say that with Francesco Soldovieri from IREA, Napoli, Istituto per il Rilevamento Elettromagnetico dell'Ambiente. And Gilles Vénetian is from Advitam. Advitam is from Vinci Group, the big construction company, and many other people. Okay, let's go. So I was pretty sure that, most of the speakers today would be able to show, the risk or the threats or the results of, seismic or other natural hazards, like scouring, for example, which occurs quite often, and well, scouring is responsible for something like 20 bridge failures every year all over the world. So it's really, so you see on the right what happens to a bridge which occurred such a scouring in Taiwan, for example. And this is what happened when flood occurred, and we heard from Claudio Moroni that there is a network of sensors which in principle predict on the short-term basis what will happen in case of heavy rains. This is in France, and so this is a threat not only on the structure and so on, but also on the people. This is a people-centric point of view, and also network operator disruption. At the bottom, you see two slides from Minneapolis. Minneapolis is really an example where, this disaster could have been avoided. Would you have placed, sensors and associated algorithms? There's a combination of factors from Minneapolis, starting with, some corrosion which was not seen by inspection, but also there were, public works on part of the bridge, and these works generated additional loads, but no one was able to estimate, to assess these additional loads. And this additional load plus traffic was too much. Okay, so an emblematic example of what could potentially be avoided in the future, and well, these consequences are not only on the structure and on the people, but also on the network operation, because network operation is broken or disrupted for quite a long time. I will show some ways to cope with this kind of network disruption. Next. Okay, networks and cities. Well, not only you have, roads, bridges, and transport, but you also have water networks. It is in Tucson, in Texas. So a big pipe broke, and the population was without fresh water for several months, for a very long time. So it's very annoying. And at the bottom, you have another kind of threat, like jam and pollutions, which will not kill you straight away, but which will kill you step by step. Okay, so it's another kind of risk, I would say, which really you have to monitor also. And really, the cost of pollution, all in all, over the world is something like $17,000 billion. You see, so it's not. It's quite enormous. So there are many challenges for monitoring, because the first challenge for monitoring, as was said this morning, that monitoring is a component of a general system to help you with resilience. But monitoring per se will not prevent failures. You have to add, a decision a support system. You have to take action also, and to be able to take action, because if you don't take action, it will not change anything. And you have to take action on a short-term basis, but also on a long-term basis. So there's a whole life cycle analysis. And monitoring is part of this life cycle analysis. The cost. You cannot place sensors everywhere right now, because the cost of sensing right now is a bottleneck for deployment. It's cost of sensing and cost of deployment, because maybe the hardware doesn't cost so much, but it is so complicated to place sensors, to go on site, especially for offshore structures, you see. There's also a lack of clear business model for that. Who really wants, well, especially maybe in countries where it is mandatory for saving thousands of lives. So it's clear that you have to monitor something. But on every country you have a forgotten asset. So a gigantic asset, infrastructures, for example. I will show some examples for which, well, nobody really wants to pay, and which is very dangerous for people and for a network operation. And part of the story that very often there is no insurance mechanism, except maybe for PPP, so private-public partnerships, where companies are responsible for operating over a certain period. Therefore, they have to be serious about the capacity to operate, and therefore they usually do something with high-tech materials and monitoring. Another aspect that, assume you can place a sensor. Can you place billion of sensors? You see, maybe you have to change your point of view, or the way you consider getting information. So, upscaling to the network scale, to a territory scale, this is really an issue, I should say. Another point is following paradox. More sensors doesn't mean more information, especially if you compare sensor outputs. So you get many data if you compare sensor outputs with physical models. You see, so it seems to be a contradiction, but it's some well-known paradox, for example, in meteorology, in 4D VAR, so to speak. So, and people say, okay, if we use models, don't use too many sensors, because too many sensors hurt our models. Okay, so so you have to be very clear about that. It's not that easy to extract information from a huge collection of sensors. Sensor placement, how to reject environmental perturbations, because temperature, as today, is wonderful. It doesn't hurt the sensors. It hurts, I mean, the physical behavior of the structures, for example. A bridge will not behave in the same way. For example, its frequency will change. Even though the sensor has a thermal correction, it's not a matter of sensors, it's a matter of the system itself, you see? So you have to monitor and to get information for the system under nominal conditions, which is another issue. And how to take the best of models, algorithms, and how to take care of the non-linearities. These are questions right now. So there are also very many opportunities right now, and we should, in my opinion, take advantage of these opportunities. First of all, you have prefabrication. For construction materials, for prefabricated bridges, for example. You have not so many such bridges, but more and more structures are prefabricated, and it is, relatively easy, to embed sensors during the fabrication process. You see, and if you do that, well, you end up with a structure which is, built-in monitored. Huh? You don't have to go with additional hardware. The hardware is still there. It's there from the origin. Another opportunity has to do with the way you consider a monitor in the value chain. You see, when it comes to durability, okay, well, maybe it will be useful to know whether your structure will last 50 years or 60 years or 70. Maybe it's useful, for sure. But sometimes structural health monitoring can be viewed as an operation critical technology because it will save money right now, not in 20 years, but now. And I will show some examples. But for example, if you want to have maintenance-free structures, if you, for example, your train operations rely on a structure which is never maintained or not so often maintained, therefore you have to check that your infrastructure is able to sustain, to support, the tracks, the trains, etc. Okay, as opportunities is maybe the multi-scale approach from, satellite point of view, which can embrace a whole territory, to, nanotechnologies, which will give you a very local information on your system. And in between, you have all airborne sensing. And if you combine everything, you end up with, what we were able to do with, especially with IREA, Napoli, the East Time project, which I will allude to. And also right now, as far as, inverse modeling or getting information from models is concerned, you can take advantage of reduced order modeling like PODs, PGDs, etc. So this is technical, I will not enter into the details, but there are novel ways to compute what you have to compute from the data. We had the chance to work with operators. So this is really a part of the roundtable. Huh? This part, it's a contribution to roundtable. We had a chance to work very closely with end users, like highway operators, ASF, so the French Autostrade, per l'Italien, and also airport owners and operators. And so the question was, what is the most important part of the asset to monitor? If you had something to do, what would you do? And they ended up with this list. The list could be different with different end users, of course, but first of all, the pre-stress level for pre-stressed bridges. Well, in France, we have many pre-stressed bridges. So it came first, and it's very tricky because, for example, when you pre-stress a beam, then of course, if it is damaged, you may not see it because it will be hidden by the pre-stressing. So there is some tricky interaction between pre-stress and damage. scour, which comes at a reasonably good place, and also something like gantries or porticos on highways, the forgotten asset. You have tens of thousands of such porticos on highways, and they are actually very dangerous for people because sometimes they fall down, and if they fall down on a car, people will die, you see? And nobody cares about that, usually. Well, so it's tremendously important. It's relatively cheap. There is usually no monitoring. So this is a forgotten asset. So if we want to recast, a monitoring system or monitoring activity, I would, well, forget about everything except maybe this state representation. So every system, or virtually every system, physical system, can be represented like this, where X, the state, of course. If you consider mechanical system, then you will have boundary conditions and sometimes some pre-stress. You will have some sensing device and some action, some active or passive control, or semi-active control, whatever, and external loads, okay? And what you will measure will be denoted by C. This will be the information which is available. And, well, no matter what algorithm you use, at some point or another, you will try to minimize or to have the observation, predicted observation. This is what you would predict from the model, as close as possible to the data that are actually measured. Okay, and you have many ways to do that. So in the blue part, you have several algorithms, like, inverse modeling. You also have stochastic subspace residual, which was developed especially for ambient vibration monitoring, and also other approaches which are not physical, which are based on data mining. All these approaches can be combined. And on the other side, you have the sensors, innovative sensors, of course, and wireless platforms whenever possible, and that's it. Okay, so the idea is that really, if you want to extract information from a monitoring system, you need, good sensors or sufficiently good sensors. You need some kind of modeling whenever available, and you need algorithms. So there is a triptych or tripod. So this is the outline of my talk. I have 20, how many? 15? 15? 20 minutes, okay. So I will start with a topic which might be somewhat complex, which has to do with the way to to identify simultaneously the pre-stressing level of a pre-stress beam, for example, and the potential damage. And to do that, we use, modeling, and the modeling, okay, you don't need to look at the equations, but, well, you can look at the equations, of course, but you're not required because it's quite, complex to comment. But first comment is that you consider, the static, strain level, which comes from the pre-stress, okay? And on top of this, deformation or displacement field, you will put some dynamic component, dynamic effect, which is due to, external loads, okay? And of course, if you sum up the static strain and dynamic strain, you will end up with a total strain, okay? So basically, you have two systems, and the dynamic equation reminds of the static problem by means of this pre-stress component, pre-stress stress here component. Okay. Now to compute, to minimize the functional, to minimize the data misfit, what really you have to do is to try to put to work a decent algorithm, a gradient algorithm, Levenberg-Marquardt, or whatever algorithm pleases you. But to do that, whenever you have a model, there is a standard way of computing the gradient, and the gradient is given by the so-called adjoint equation. The adjoint equation is nothing but the original equation where now the sensors, because you have sensors, now play the role of actuators. That's how, consider your sensors are actuators, and at these actuators you have some pointwise loads, okay? and you solve the problem. This is the adjoint equation. Combining the two, you have, ugly expressions of the gradient, and you can compute everything, in this case, by means of taking advantage of high-level softwares like Python environment, in which you can really program your high-level algorithm, and professional finite element codes, which, for example, engineering companies know finite elements. And we have a way to couple, what comes from research with what is used in the companies. And this is a way to do that, because it was our goal to do that. And the result is that it works. This kind of system of approach works. SCOUR. Now I go to SCOUR. SCOUR is very important, and SCOUR can be formulated like this. You have a structure like a beam. This is a simplified pile, of course. And here you have some kind of stiffness. So the foundation can be replaced by some parameter which reflects, so to speak, the stiffness. This is if you know that it's the Winkler-Westergaard foundation, it doesn't matter. This is the stiffness. And by carrying out sensitivity analysis, well, if you are able to monitor the vibration, the eigenvibration changes, which I call here delta omega, that is a formula which we can pre-compute with the finite element common. You can pre-compute this formula, and you have the variation of the resistance of the foundation, you see? So the stiffness of the foundation is related to the frequency with formulas that you can compute in advance by using this kind of finite element code. And you can even get values. This is for per-Orad bridge. This is real life monitoring. Okay. Porticos, well, it turned out that Portico is something very simple, actually. It's something like a mass spring system. And therefore, well, we carried out some experiment also with ad vitam in the framework of this Cyprus project, and we simulated damages. We will also, cut some part of the Portico. This is in Nantes, where you will go in July. And so you will, whoever attends EWS HM 2014 will see that. So we are all welcome in Nantes because we organize this workshop. If you place an added mass, a small one, because it's a gigantic structure, so this is 70 kilos or something, well, you see a drop in the frequency. And the temperature doesn't change much, you see? So it's a structure which is intrinsically non-sensitive to environmental perturbations, and for which you have a clear frequency shift whenever you have a damage. So it's a perfect type of structure for implementing ambient vibration monitoring. This is absolutely perfect. It's just like maybe a one-story building, if you want. Okay, let me go very quickly to railway tracks. Well, and I will go very fast with the rest, of course, because I will not have time to give too many details. But this is really this is another private-public partnerships, which resulted in novel concrete tracks, concrete railway tracks, which are very thin. A concrete track has the advantage of requesting no maintenance with respect to, ballasted tracks. So almost zero maintenance. Therefore, you can really shift or operate a modal shift from the road to the rail. The shift to rail initiative is based on concepts like that. But now, if you want the track to be available at any time, then you really have to monitor carefully. And here, monitoring is, operation critical. The result is this real track here, which was built only 5 years after the research began. You see, so it took 5 years from, the white paper, because this structure is completely novel. Huh? Well, because usually, concrete railway slabs are very thick. This one is very thin, so it's very innovative in some aspect. So it was one with Alstom, Railtech, and I mean big companies, and it is entirely monitored on site, really. Huh? And the idea is that I mean a Brillouin type of fiber optical system yields, and it has been validated at the lab. It yields a continuous pattern of the strains. Okay, and it works. Okay, I will skip the details. I will skip all this because what I want to show maybe is development of a wireless platform which has been which is quite general and which has been customized for freeway operations like way in motion and structural condition, but also for water networks, smart water networks, you see. So this is a generic platform which has been licensed to a company and which is now sold quite broadly. Another concept is the prefabricated bridge. You see, this is quite a long, well, it's a short bridge, but every, big beam is only 240 kilograms. So this is something that you can carry with several people, you see. So this is something you can put on your truck whenever another bridge collapses. So you put this bridge on your truck and you can go to the site, and after a few days or maybe a short time, maybe a week, you can have a new bridge, with maybe reduced capabilities. And this kind of composite bridge is intrinsically monitored by ultrasonic sensors, by relay sensors for continuous strains, etc. Okay, I skip this. I will skip this. This is the East Times project with the coupling of synthetic aperture radar, which gives you an idea, a global idea of a territory, and also a very fun one. Multispectral analysis, which is airborne, thermored infrared thermography, and also optical fiber sensors and many others. So you can find that, but the good idea is that you can really monitor at once, a whole structure from the sky, with Terasa X type of sensing devices. So I will skip this. This is another kind of electrical tomography. I will skip this maybe. And yes, I come to another way of conceiving sensors, which is nanotech. For example, the extensive use of nanotechnologies can result in very novel sensors for which the unit cost can be very small. Okay, so the idea is really to kill the cost. So it's a cost killer. It's not just for putting nanotubes everywhere. So we don't care about that. But an example, and I show you only. So it was patented quite recently, but a novel way in motion or load monitoring sensor. This is a load monitoring sensor, which is made of graphene sepulite, which is clay, essentially clay, and nanotubes. So everything's doped, and you end up with a sheet which is compatible with construction materials. So you can really put that in asphalt and so on. So it's completely compatible with asphalt, and it works because it features piezoresistivity, interesting piezoresistivity, and therefore this is distributed, strain sensors, which you can produce. There is a process, you see. So, okay. I'm almost finished, maybe two minutes right now. I will not really comment on that, but there is a recent or relatively recent result regarding inverse modeling, or the way to extract information from the sensors. When you want to solve, for example, the minimization of the data misfit, when you want to minimize the data misfit, this is equivalent to solving another problem for which you have finite element approximation with a mesh made with a node where you have sensors. So at every sensor location, you put a node, you create a mesh, you create a P1 Lagrange approximation, and you have, a dual problem, which is equivalent to the original one. Therefore, sensor placement can be viewed as a way, to increase, the accuracy of the way you solve your inverse problem. Therefore, inverse problem and sensor placement is equivalent to solving, a mesh refinement problem. You see, and you can also explain by that if you have too many sensors, then maybe you will have, an ill-pose problem. It's quite classical in finite elements. The more you refine, well, sometimes you have, you have a lack of coercivity or cohesiveness, as they say in Pavia. Huh? It was. It originated from Pavia. And this explains that the more sensors you have, the more sensitive you are to sensor uncertainties, etc. Okay, and well, last but not least, I have to finish with that well, whatever we do in monitoring is indebted in, our great masters, Galileo Galilei. Thank you very much.